In a massive industrial port yard, thousands of heavy ship anchor chains are stored in enormous piles stretching across the facility. These chains are made of thick forged steel, designed to hold ships in extreme ocean conditions. But now they are completely decommissioned and covered in layers of rust, salt deposits, and marine residue. The environment is wet, heavy, and industrial, with seawater still dripping from the metal surfaces after long exposure at sea. Huge automated crane systems dominate the area, moving slowly but powerfully as they lift entire sections of chains using magnetic grips and mechanical hooks. Each movement is controlled with precision to handle the extreme weight of the material. Conveyor systems beneath the cranes continuously receive and transfer the chains deeper into the processing line. After collection, the massive ship anchor chains are transferred into reinforced industrial containers built specifically for extreme heavy-duty transport. These containers are loaded using automated conveyor arms and crane systems that carefully distribute weight to maintain balance. Once fully loaded, specialized transport trucks begin moving along controlled industrial routes toward the recycling facility. Each truck is engineered to carry extreme loads without structural instability. The chains remain tightly packed, still retaining their original rusted, corroded, and ocean-worn appearance. During transport, stabilization systems ensure that no shifting or movement occurs, even under vibration or terrain changes. Their journey passes through structured industrial corridors filled with steel frameworks, pipelines, and large-scale manufacturing infrastructure. At the recycling facility, the ship chains enter a fully automated material sorting system. The chains are first placed onto vibrating conveyor platforms that shake off loose debris such as mud, sand, and marine buildup. From there, rotating drum separators and mechanical screening systems divide materials based on size and density. Advanced industrial sensors scan each metal section to identify composition, structural integrity, and contamination levels. Magnetic separation units extract unwanted foreign materials while ensuring only high-grade steel chain segments proceed further. Every piece is analyzed in real time to maintain strict quality control standards. Defective or heavily damaged sections are automatically diverted into secondary processing lines. The sorted ship chains are transferred into a high-pressure industrial cleaning chamber designed to remove years of marine contamination. Inside the chamber, powerful water jets are activated in synchronized patterns, blasting every surface of the chains with extreme force. The chains rotate slowly on mechanical rollers, ensuring that every angle is fully exposed to the cleaning system. Layers of rust, salt deposits, oil residue, and marine growth are gradually stripped away under continuous pressure. The cleaning process is intense and sustained, producing large amounts of contaminated runoff water that is immediately collected and filtered through industrial recycling systems. After cleaning, the ship chains are fed into a hydraulic cutting system designed for extreme industrial steel processing. The long continuous chains are far too large for direct melting or shredding, so they must first be segmented into manageable sections. Massive hydraulic blades descend with controlled force, cutting through thick steel links with precision and consistency. Each cutting cycle is carefully synchronized to maintain uniform segment lengths across all processed material. The system operates continuously, feeding new chain sections into the cutting zone without interruption. Sparks and mechanical stress are contained within reinforced cutting chambers to ensure safe operation. Once cut, the chain segments are immediately transferred onto conveyor systems that move them forward to the next processing stage. This step is essential because it prepares the dense marine-grade steel for mechanical fragmentation, ensuring that the material can be efficiently processed in shredding and melting systems downstream. The cut segments of ship anchor chains enter a high-power industrial shredder system. Inside the machine, multiple rotating steel hammers and crushing blades operate at extreme torque levels. The purpose of this stage is to completely break down the structural integrity of the chain segments. Each impact fractures the steel into smaller, irregular pieces, gradually reducing them into coarse metal fragments. The entire process takes place inside a sealed, reinforced chamber designed to contain noise, vibration, and metal debris. Conveyor systems continuously extract shredded output and transport it forward without stopping the production flow. At this point, the original identity of the chains begins to disappear completely, replaced by raw fragmented steel material. This shredded output is now in a form suitable for high-temperature melting, marking a major transition from mechanical destruction to metallurgical processing in the recycling chain transformation system. The cut segments of ship anchor chains enter a high-power industrial shredder system. Inside the machine, multiple rotating steel hammers and crushing blades operate at extreme torque levels. The purpose of this stage is to completely break down the structural integrity of the chain segments. Each impact fractures the steel into smaller, irregular pieces, gradually reducing them into coarse metal fragments. The entire process takes place inside a sealed, reinforced chamber designed to contain noise, vibration, and metal debris. Conveyor systems continuously extract shredded output and transport it forward without stopping the production flow. At this point, the original identity of the chains begins to disappear completely, replaced by raw fragmented steel material. This shredded output is now in a form suitable for high-temperature melting, marking a major transition from mechanical destruction to metallurgical processing in the recycling chain transformation system. The molten steel coming from recycled ship anchor chains enters a large-scale refining ladle system where its quality is carefully controlled. At this stage, the metal is still in a fully liquid state, glowing intensely under extreme industrial heat. The refining process begins with precise chemical balancing. Oxygen is injected into the molten steel to remove excess carbon content and unwanted impurities that could weaken the final product. At the same time, carefully measured alloying elements are added to adjust strength, hardness, and flexibility, depending on the required industrial specification. Massive mechanical stirring systems keep the entire molten mass in constant motion, ensuring that every part of the steel has a uniform composition. After the refining process is completed, the purified molten steel is transferred into a continuous casting system designed for large-scale industrial production. The glowing liquid metal flows steadily into vertical molds, where it begins the transformation from liquid to solid form. The cooling system surrounding the molds is carefully calibrated to control the solidification rate, ensuring that the internal structure of the steel forms evenly without cracks or stress points. As the process continues, the molten steel gradually solidifies from the outer surface inward, creating a strong and uniform structure. The material slowly moves downward through the casting line as more molten steel is continuously fed from above, forming an uninterrupted production cycle. The newly formed steel billets are transferred into a controlled cooling zone designed to stabilize their internal structure. At this stage, temperature management is extremely critical because uneven cooling could lead to internal stress or micro cracks that would weaken the final product. Large industrial air blowers and water mist systems work together to gradually reduce the temperature of each billet in a highly controlled manner. The cooling process is slow and evenly distributed across all surfaces to maintain structural integrity. As the steel cools down, its molecular structure becomes more stable and stronger. Automated conveyor systems continuously move the billets through the cooling line without interruption, ensuring constant production flow. The cooled steel billets are now moved into a high-temperature reheating furnace where they are prepared for mechanical shaping. The furnace gradually raises the temperature of the steel until it reaches a precise forging range. This is not melting, but controlled heating that makes the material soft enough to be shaped under extreme pressure. As the temperature increases, the billets begin to glow bright orange, indicating that their internal structure has become malleable. The heating process is carefully controlled to ensure uniform temperature distribution across every piece, preventing uneven deformation during forging. Conveyor rollers continuously transport the billets through the furnace, maintaining a steady production flow. At this stage, the steel is no longer rigid, but not yet formed into its final shape. It is now in a transitional state, ready to be reshaped into mechanical gear components in the next phase of production. The heated steel billets are transferred into a massive hydraulic forging press designed for extreme industrial force. Once positioned, the press delivers powerful compressive strokes that reshape the steel into rough gear blanks. Each impact not only changes the external shape, but also restructures the internal grain of the metal, increasing its density and mechanical strength. The forging process is repeated in controlled cycles, with automated systems repositioning each billet between presses to ensure even shaping from all angles. Although the form is still rough and unfinished, the basic geometry of a gear begins to appear. This stage is essential because it defines the structural foundation of the final component. The steel that once formed heavy ocean-used chains is now being reshaped into a completely new industrial identity as a mechanical gear blank. Forged gear blanks are transported into high-precision CNC machining systems for detailed shaping. These computer-controlled machines operate with extreme accuracy, removing small layers of metal to form perfectly defined gear teeth. Each gear is rotated continuously, while cutting tools shape every detail according to exact engineering specifications. Cooling fluids are applied throughout the process to prevent overheating and maintain dimensional stability. The machining process is fully automated, ensuring that every gear produced is identical in size, shape, and performance standards. Gradually, the rough forged blanks are transformed into precise mechanical gears with fully formed teeth and smooth surfaces. This stage defines the functional accuracy of the component, turning raw forged steel into a high-precision mechanical part ready for industrial use. The precision machine gears undergo a controlled heat treatment process designed to enhance strength and durability. Inside specialized industrial furnaces, the gears are heated to extremely high temperatures until their internal structure becomes fully responsive to transformation. Once the required temperature is reached, the gears are rapidly cooled using oil or air quenching systems. This sudden temperature change alters the molecular structure of the steel, significantly increasing hardness and wear resistance. The process is carefully controlled to avoid deformation or cracking, ensuring that the precise gear geometry remains intact. After completing this cycle, the gears become much stronger and more resistant to long-term mechanical stress. This transformation is essential for ensuring reliable performance in demanding automotive and industrial environments. After heat treatment, the gears enter a surface finishing stage where precision grinding machines refine every detail. High-speed abrasive tools carefully polish the gear teeth and remove any microscopic imperfections left from previous processes. Each gear rotates slowly while the grinding system applies controlled pressure to achieve perfect surface smoothness. Cooling systems operate continuously to prevent heat buildup during finishing. The goal of this stage is to ensure perfect alignment and smooth mechanical interaction between gear components. As the process continues, the gears achieve a highly polished and uniform surface. This final refinement ensures that the gears can operate efficiently, quietly, and with minimal friction inside mechanical systems. Every finished gear undergoes a strict automated quality control inspection process. Advanced laser scanning systems measure each component with extreme precision, checking dimensions, tooth alignment, and surface accuracy. The system compares every gear against strict engineering standards to ensure full compliance. If any deviation is detected, the defective gear is automatically removed from the production line for reprocessing. Only components that meet all specifications are approved for further use. This stage ensures consistency, reliability, and safety across all manufactured gears. The inspection process runs continuously, maintaining high production quality without interruption. At this point, the gears are confirmed as fully functional industrial components ready for protective coating. Approved gears move into a protective coating chamber where an anti-corrosion layer is applied. This coating process is designed to protect the steel from rust, moisture, and long-term environmental damage. The gears rotate slowly during application to ensure complete and even coverage across all surfaces. The protective layer bonds directly to the metal surface, forming a durable shield against oxidation. After coating, the gears pass through a controlled drying system where the layer is cured and permanently stabilized. This ensures long-lasting protection even under extreme operational conditions. Once completed, the gears are fully protected and ready for integration into mechanical systems. Coated gears are transferred into an automated transmission assembly system where robotic machinery handles precise installation. Each gear is carefully positioned inside the transmission housing according to exact mechanical alignment requirements. Multiple gears are assembled together to form a complete transmission system that operates as a unified mechanical unit. The process is fully automated to ensure speed, precision, and consistency. As each component is installed, the system becomes more complete and functional. This stage transforms individual gears into a fully operational transmission system ready for real-world application in vehicles. The completed transmission systems undergo rigorous functional testing in a controlled industrial environment. The gears inside the system are set into motion under varying load conditions to simulate real operational stress. Sensors continuously monitor vibration levels, rotational speed, torque output, and mechanical stability. The system runs through extended cycles to evaluate long-term durability and performance reliability. Any irregularities are detected instantly and analyzed for correction. This testing phase ensures that every transmission system meets strict engineering standards before installation. It confirms that the recycled ship chain steel has successfully transformed into a reliable, high-performance mechanical system. After passing all tests, transmission systems are transported to automated vehicle assembly lines. Robotic systems carefully install each transmission into vehicle chassis with precise alignment. The integration process is fully synchronized to maintain continuous production flow across the factory. Each transmission becomes a core component of the vehicle's drivetrain system. This stage represents the final integration of engineered mechanical systems into functional transportation units. The gears that once existed as heavy marine chains are now part of modern automotive technology. Vehicles equipped with the recycled gear transmission systems enter automated performance testing tracks. These systems simulate real-world driving conditions, including acceleration, braking, load resistance, and continuous operation cycles. Every movement of the vehicle is monitored through advanced digital sensor systems. Data is collected in real time to evaluate efficiency, durability, and mechanical stability. The testing process ensures that the transmission performs reliably under various stress conditions. This final evaluation confirms the success of the entire transformation process from raw ship chain material to functional automotive systems. Completed automotive systems are stored in large industrial warehouses awaiting distribution. Rows of finished transmission units are carefully organized in structured storage systems. Each unit represents the final result of a long industrial transformation process that began with discarded ship anchor chains. Through multiple stages of recycling, refining, forging, and precision engineering, the material has been completely transformed into high-performance automotive components. This final stage represents the completion of a full industrial cycle, turning marine waste into valuable mechanical technology used in modern transportation systems.